So we understand why the planets are orbiting around the sun the way they do, but we still need to be able to explain why there are two types of planets as well as where asteroids and comets come from. So why is it that there are two types of planets? Well, we see that part of it is that they are made up of different things, so we need to start with composition. The solar nebula, the nebula that eventually formed into the solar system, had the same composition as the rest of the universe. So if you remember previously, this is going to be about 74% hydrogen, 24% helium, and about 2% everything else. Well, something else we need to take into account is at what temperature things are able to condense. What we mean by condense is something else that we need to consider is at what temperature different materials condense. What we mean by condense is having it go from a gas into being a liquid or solid. Considering the properties of the solar nebula, it's most likely to form into solids. Now, looking at different materials at different temperatures, metals have a very high condensation temperature, meaning that even at very high temperatures they're able to form into solid pieces. Rock is similar, although slightly cooler. And then hydrogen compounds. What we mean by hydrogen compounds are things like water, methane, and ammonia. These actually have very low condensation temperatures, which means it has to be very cold for these things to start forming into solids. Now, something I want to point out is that hydrogen and helium will never condense. Under the conditions of the solar nebula, hydrogen and helium will always remain as a gas. As we look at the temperature difference throughout the forming solar system, we know that at the center around the protosun it's going to be very, very hot. Then as we move out towards the edge, it's going to get cooler and cooler. At some distance away from the sun, we're going to form the frost line. The frost line is this transition where it finally gets cold enough to allow ices to form. Now remember, ices are things that are normally liquids and gases under conditions on the Earth, but are so cold they're frozen. So these are going to be things like frozen water, frozen ammonia, frozen methane, the frozen hydrogen compounds. So inside the frost line, it's very warm, meaning that metal and rock are able to condense, but not ices. Beyond the frost line, it cools off enough that you're able to form rock and metal still, as well as ices. Now, as these pieces are forming, they're going to begin by forming tiny little flakes. Kind of the way that I think about it is how snowflakes form within clouds. As the clouds cool off, the water in the clouds freeze, forming flakes which swirl around. This is the process of condensation. Then these flakes will occasionally bump into each other, and as they do, they can then stick together, growing larger. This is the process of accretion. Accretion is this slow buildup, growing larger and larger and larger. So again, it's similar to snowflakes. If you've ever been in one of those snowstorms that has the really big snowflakes, if you actually look at them, they're not a single snowflake, they're a whole bunch of snowflakes that have stuck together. Again, this is the process of accretion. Now at first, these bumps are going to be random chance. However, over time, as they grow larger and larger, they'll have more and more mass, until eventually gravity starts helping pulling these things together. Now once these objects get about to the size of asteroids, so hundreds of meters to hundreds of kilometers across, we refer to them as planetesimals. Planetesimals. So at one point in the solar system, we had millions and millions of planetesimals orbiting around the sun. Because there were so many, they had a strong gravitational pull on each other, constantly changing their orbits, leading to more and more frequent collisions, allowing these things to merge together. So after a while, instead of millions and millions of planetesimals, we then settle down to several dozen protoplanets. Protoplanets are things on the scale of Mercury to Mars to possibly even the Earth. So we have a lot of these, but now they're much larger. Now, because there's still a lot of these, they're going to still have relatively chaotic orbits, leading to more mergers, until eventually we are left with just a few planets that have swept up most of the material and are now on nearly circular, stable orbits. We actually have evidence for this process by looking at meteorites. A meteorite is a chunk of rock from space that has actually landed on the Earth. Some of the very oldest ones of these are chondrites, which, instead of having a uniform composition, are actually made up of chondrules, these small flakes of other materials that have welded together. Here is our second lecture quiz question. What could condense in the outer solar system? By outer solar system, we mean far from the sun. A, metal and rock, B, water and methane, C, hydrogen and helium, or D, both A and B. Go ahead and think about it and we'll discuss in just a bit. So what can condense in the outer solar system? Well, everywhere throughout the solar system we're going to be able to make metal and rock. Those things have very high condensation temperatures, which means pretty much everywhere throughout the solar system it's going to be cool enough to allow rock and metal. When we get to the outer solar system, it gets very cold. It gets so cold that now water and methane are going to be able to condense into solids. So beyond the frost line, we actually expect the answer D, both metal and rock and water and methane. So again, the correct answer is D. So in the outer solar system, we get rock metal as well as ices, which means we now have more stuff that we can use to make planets. And if there's more stuff we can have to make planets, that means the planets are going to get bigger. So in this process of accretion, we expect to form this rocky, icy core. But it gains so much mass that it's actually able to start drawing in hydrogen and helium gas. Remember, hydrogen and helium do not condense in the solar system. So these pockets will pick up more and more hydrogen and helium, which means they become more massive, which allows them to draw in more helium and so on, until these planets have a large hydrogen and helium atmosphere. This makes the Jovian planets that we see today. As these Jovian planets are forming, they actually have enough mass that they pull in a lot of material around themselves, similar to how the proto-sun had the protoplanetary disk. So we have the Jovian planet with a proto-moon disk surrounding it. So we have the Jovian planet with a proto-moon disk surrounding it. It's within this disk that some of the moons can actually form. Now, if you remember back when we talked about Galileo's evidence for a heliocentric solar system, he pointed to Jupiter and how Jupiter's moons appeared to orbit around it, similar to how the heliocentric model said that planets orbit around the sun. Well, this analogy works all the way down to how the moons formed. Some of the Jovian planet's moons formed through condensation and accretion around the planet, just like the planets form through condensation and accretion around the sun. Now, this also helps us explain where asteroids and comets come from. Not all of the material that was able to condense actually got swept up, forming into planets. In the inner solar system, this is the region where we'd have rock and metal, so this is where asteroids come from. Asteroids are the pieces that didn't get swept up into the terrestrial planets in the inner solar system. Comets are both rocky and icy, which means they are the leftovers from beyond the frost line in the outer solar system. Now, as the sun turned on, going from protostar into full-fledged star, it began the solar wind. The solar wind then began to push out anything that remained as a gas within the solar system. This will then reveal the solar system as it is. In this image, we have a cluster of some young stars, and you can see that they are pushing back the nebula with their stellar winds. Now, one problem we have is that the Earth formed in the inner solar system, which is where only rock and metal could survive. Remember, we do not have ices in the inner solar system. Ices form beyond the frost line. And yet, we know that the Earth has water. So exactly how did the Earth get water? Well, we believe that there is this period in the early solar system where the Earth kept getting hit by stuff. Specifically, there were comets in the outer solar system that got thrown in towards the inner solar system. This time is referred to as the period of heavy bombardment. Based off of current understanding, we think that this period occurred because of motion of Jupiter. And that motion of comets towards the inner solar system brought the water that we now see on Earth. Here is our third lecture quiz question. Why are there asteroids and comets? A planet exploded due to chemical reactions in the core. B, these are leftovers from when the planets were accreting. C, they are evidence of interactions between two planetary systems colliding. Or D, it is the leftovers of a planet destroyed through intergalactic war. Go ahead and think about it, and we'll discuss in just a bit. Alright, so where do asteroids and comets come from? The correct answer is B. These are the leftovers from when the planets were still accreting. This is the stuff that the planets were not able to sweep together. And here's our fourth lecture quiz question. How would the solar system be different if the solar nebula had cooled with a temperature of half its actual value? A, Jovian planets would have formed closer to the Sun. B, there would be no asteroids. C, there would be no comets. Or D, terrestrial planets would be larger. Go ahead and think about it, and we'll discuss in just a bit. Alright, what do you think? How would the solar system be different if the nebula had cooled with half its actual value? I'm going to argue A is the best answer. So if the whole solar system was cooler, that means that the frost line would get moved in closer towards the Sun. We form terrestrial planets inside the frost line, and then we form Jovian planets outside the frost line. So if the frost line is closer, Jovian planets would also form closer to the Sun, so A is going to be the best answer. The last thing that we have to explain are exceptions to the other rules. Well, in a lot of cases, large impacts actually explain those exceptions. So, for example, Uranus being tipped over on its side. If it got hit early on, as it was still forming, got hit really hard, then it could tip it over on its side. One of the surprising features of Mercury is that it has a very high iron content compared to the other terrestrial planets. We'll see this later when we talk about Mercury, but one possible explanation is that it got hit really hard. Venus, as we mentioned previously, rotates backwards. One explanation for this is that it got hit really hard, so hard that it caused it to start spinning backwards. Often, our go-to explanation with anything weird with the planets is that it got hit really hard early on during the process of formation. Now, there are some things that we're not going to be able to explain with the idea of a giant impact. Most of these are moons with retrograde orbits. Remember, retrograde means backwards, orbiting backwards around the planet. Now, generally, we expect moons to orbit in the same direction because of conservation of angular momentum. Moons that formed around a planet will go in the same direction that the planet is rotating. But we find some moons that are orbiting backwards compared to the direction the planet is rotating. This is a retrograde orbit. Our best explanation for retrograde orbits of moons is capture. That these were actually asteroids or comets that got too close to the planet and got captured by the planet's gravity, turning them into moons.